Hi class, welcome to exercise 6b, Pythagoras Theorem. In today's class, your examples will be example 4, finding side lengths using Pythagoras Theorem. And your pre-learning for this will be questions 1, 2 and 3 in the new book and questions 3 and 4 in the old book. Sorry about that, Nick. I know you don't like the extra questions in the new book. And then we'll do example 5, which is using Pythagoras Theorem in 3D. And your pre-learning for this will be questions 4 in the new book and questions 5 in the old book. At this stage, clearly Pythagoras Theorem is not new to you. However, by the time you have completed all the work in this lesson, with confidence prove why it must be true. You'll also learn how to apply it to distances in 3 dimensions. You've already used the Pythagoras Theorem this year with the distance function, but hopefully you'll see that we can use Pythagoras Theorem to find the distance between any points in a Cartesian coordinate system of any dimension. Cartesian coordinates is just one where you can have a space described by axes that are perpendicular to each other. The xy axis that we've used is called the Cartesian plane. I'm going to introduce 2 ways of showing you why Pythagoras Theorem is true in the introduction. However, I'll leave them as incomplete and expect you to complete them. Because following this video, I'm going to make an extra video with 3 challenges in it. This will be those 2 proofs of Pythagoras' theorem, and another one where we're going to use Pythagoras' theorem to estimate pi. Okay, let's get on with the introduction. I'll demonstrate how to find side lengths and the application of Pythagoras' theorem in 3D in the relevant sections. In this introduction, we're just going to look at the beginning of proofs that you'll complete at the end of the lesson. But before we begin, we must state that Pythagoras' theorem applies to right angle triangles only. So if we have a right angle triangle, then the length of the hypotenuse squared is equal to the length of one side squared plus the length of the other side squared, which is famously known as c squared is equal to a squared plus b squared. Let's have a quick look at this in GeoGebra using this applet. Well, here you can see a right angle triangle with sides A, B and C being the hypotenuse. These squares represent the square of the side length that it's attached to. Notice how a squared plus b squared equals 7.5 plus 8.4 is 15.9, 15.95, which is almost the same as c squared, which is 15.94. The only difference is that we're dealing with irrational numbers and estimating at 2 decimal places. If I move these dots around, I've created a different right angle triangle, but still a squared plus b squared is 13 plus 7 is 20, is 20.65, which equals c squared. So it doesn't matter how you move this around, the sum of these 2 squares will always equal the sum of the bigger square. Okay, back in OneNote now. As always, you're welcome to play with that applet anytime you want. But one fun fact we need to remember about right angle triangles is something that's called the triangle inequality, which is for any right angle triangle with hypotenuse C and side lengths A and B, C will be greater or equal to A and B, but A plus B is always going to be greater than or equal to C. This is a very important fact for Pythagoras and for trigonometry. Okay, let's get on to showing why Pythagoras is always true. Okay, for the first one, let's draw a right angle triangle with side lengths A, B and C. Now we're going to copy that and rotate it by 90 degrees. And we'll copy it again and also rotate that by 90 degrees. And again, and rotate that by 90 degrees. And we'll copy that original one more time. Now I'm going to slide these down below the screen. And then I'm going to copy them all again. Now why would I want these 8 triangles? Well, let me just move around these arrangements of them and draw a box around the second arrangement. And now I'm going to colour in these triangles. Now believe it or not, this is a proof that Pythagoras has to be true. In the challenges you have to demonstrate why all 3 blank spaces are squares and what their areas are. You also have to show what the area of the containing spaces are and the area of the triangles. I suggest that you wait for the challenges in the next video But here is a GeoGebra applet to show you how this is true for all right angled triangles. Alright, so I made this applet to make sure you can see that it wasn't a fluke that I chose the exact right angle. This arrangement will work for any right angled triangle. So these sliders here, A and B, change the lengths of the sides of the triangle that are not the hypotenuse. So let me move those around, starting with A and then B. So the writing on this is a little small for you to read now, but if you come back into this applet later on, you can see that the sum of the smaller squares is equal to the bigger square, which I've got written down at the bottom here. And for those of you who squint or look closely, there might be some clues on how to solve this challenge later on. Now, the second way of proving Pythagoras' theorem comes from a time when US presidents weren't a walking meme about ignorance. Which is a long time ago, because it's back in 1881, soon-to-be President Garfield noticed that a trapezium has the area x plus y divided by 2 multiplied by z. When we have a trapezium that has one side x and the other side y and the base z. I'm going to change this z to a w because my z looks too much like 2's. So let's restate that this x plus y divided by 2 times w is the area of this trapezium. And we'll cover exactly how to do that in a lesson in this unit, but not this one. Then he noticed that if he took a right angle triangle with sides A, B and C and copied it twice, he could move them together and create a trapezium with one more line. So let me colour that in. Now he could calculate the whole area of the trapezium and recognise that it's equal to the sum of the areas of the triangles. And then with some algebra, he was able to conclude that a squared plus b squared equals c squared. Once again, we'll leave that for the challenges, but I have written an applet for this in GeoGebra, which you can check out at this link here. Once again, we're here just to show that the rule works for any a or b, which are the lengths of the side of the triangle that's not the hypotenuse. Now, if you look closely, you might get some good ideas how you'll solve this one in the challenge, but not as many as there were in the last GeoGebra applet. Either way, you may wish to come back and play with this yourself as you contemplate the proof. Both of these proofs are going to tie together a lot of ideas from this unit, such as geometric reasoning with congruence, similarity, quadrilaterals and angle sum, and there'll be connections between perimeter and area. Okay, so to sum up this introduction, Pythagoras' theorem makes sense of the distance function in linear relations, relies upon square roots and surds, and tells us that for every right angled triangle where C is the length of the hypotenuse and A and B are the lengths of the other sides, C squared will always equal A squared plus B squared. Okay, that's the end of the introduction, but perhaps you might want to pause the video now and start working on some building understanding questions in the new book, which relates to questions 1 and 2 in the old book. And I'll see you in the next section. You'll soon prove that it's true, but we already know that if we have a right angled triangle with side lengths A, B and C, then C squared is equal to A squared plus B squared. So recalling our work with square roots, that means that C is equal to the square root of C squared. And because C squared is equal to A squared plus B squared, we know that C will equal A squared plus B squared, all square rooted. Sometimes in the question we're given the value of C, so we'll need to manipulate algebraically. So because C squared is equal to A squared plus B squared, that also means that C squared minus A squared is equal to B squared, or C squared minus B squared is equal to A squared. And if we swap sides of this equation, we could also say that B is equal to the square root of C squared minus A squared, and that A is equal to the square root of C squared minus B squared. It's very lucky that you have mastered surds already. And while we're on surds, just make note that if the answer is a surd, i.e. square root of 8, then exact answer is square root of 8. Only convert it to decimal expansion estimation if asked. Okay, let's get on with some numeric examples in example 4, where we have to find the length of the unknown side in these right angled triangles. We also need to round each of them to 2 decimal places. In part A, we have an unknown hypotenuse and side lengths of 5 and 9 centimeters. This is a simple application of Pythagoras' theorem with x squared equal to 5 squared plus 9 squared. So x squared is equal to 25 plus 81, which is 106. So x is equal to the square root of 106. So because we're asked to find these two decimal places, we don't need to wheel out our amazing square root and surd skills. So let's just use the calculator. The square root of 106. So yeah, x is equal to 10.295 ... So the 5 makes the 9 round up. So in two decimal places, we actually say x is equal to 10.3 centimeters. All right, that's pretty straightforward. In part B, we have a right angled triangle with a hypotenuse of 1.5 centimeters and another side with a length of 1.1. So applying Pythagoras, this means 1.5 squared has to equal y squared plus 1.1 squared, which means that y squared is equal to 1.5 minus 1.1 squared. And that's 1.5 squared, I should say. Therefore, y is equal to the square root of 1.5 squared minus 1 squared. And putting that in a calculator, we have 1.019, so we're going to round that up to y is equal to 1.02 centimeters. All right, so that's it for this example. It's fairly simple. Obviously, you've done stuff like this last year. So just pause the video now and do questions 1, 2, and 3 in the new book and questions 3 and 4 in the old book. And then I'll see you in the next section. Okay, I'm going to struggle drawing a lot of this, so I'm going to rely upon using GeoGebra. So far, we've worked with Pythagoras in 2D. And 2D Pythagoras would help you find the distance between two corners on the same wall. For example, a wall that is 3 meters high and 4 meters across. If I wanted to figure out the distance between these points A and B, the distance from A to B is equal to the square root of 3 squared plus 4 squared, which is just 5. But what if we were to draw a box or a room and mark in these points A, B, C, and D? If we know what the distance is from A to B and A to C and C to D, what is this distance from B to D? Let's have a look at this in GeoGebra first, using this applet here. Here we see a point in 3D space, and this plane you can see is the XY plane, which you're already used to. And if I was to move to a certain angle, it would be just like looking at the XY plane. Now we're going to figure out the length of this line F, which is the line between A and B. First, let's add a box or room, just like the one I attempted to draw in OneNote. From this view, it looks like a square or a rectangle. So let's move to a different perspective, so it's obviously 3D. Now we can measure the length, width, and height of this room. And if I move this point around, you'll see that the box changes to fit the line. I can also move it up and down. Of course, instead of saying that the box is changing to fit the line, you could say that this line was changing to measure the box. Now we know that we could figure out the length of F, the line from A to B, with this triangle. We can see that the height of this triangle is 3.68, but we don't know how long this line G is. Hopefully you can see that we've created a right angle triangle on the floor here. So let's add that in. And let's get rid of the box so these triangles stand out a little bit more clearly. Now I've put the angles in the corners there so you can see that they're right angles. So they're definitely right angle triangles. So clearly G squared is going to equal 7.34 squared plus 7.2 squared. And because they're all involved in a right angle triangle, F squared is going to equal G squared plus 3.68 squared. So taking the square root, that means that F is going to equal the square root of G squared plus that height, 3.68 squared. Let's have a look at that formula. Now here you can see all of the lengths squared and added together underneath the square root. So why are they all in there together? Well, 7.72 squared plus 7.34 squared is equal to G squared. And then we add in the height, 3.68 squared. In the textbook, they might ask you to figure out G on its own first, but that's not necessary. You can find the formula immediately with the three lengths like this. Once again, you're welcome to use this applet to figure out things if you need to in the future. I'll put a link to all the applets used in the video description as well as the OneNote. But let's get back to the OneNote to figure out the formulas and apply this in some examples. So after looking at that GeoGebra applet, we know that we're looking for this length here, which we'll call F. And we'll use this length G to form a right angle triangle with Z and F. So this means that F squared is going to equal G squared plus Z squared. And because we know that G squared is equal to X squared plus Y squared, because they form a right angle triangle, if we subbed in X squared plus Y squared for G squared, we now get F squared is equal to X squared plus Y squared plus Z squared. So that means that F is equal to the square root of X squared plus Y squared plus Z squared. Now let's put these facts to work with numbers in example 5, where we consider a rectangular prism with corners A, B, C, D, E, F, G and H with side lengths 7, 4 and 2. In part A, we're asked to find BE and leave our answer in exact form. So BE is obviously this green line. So using Pythagoras' theorem, BE squared is clearly equal to 7 squared plus 4 squared. Therefore BE is equal to the square root of 7 squared plus 4 squared, which equals the square root of 49 plus 16, which is equal to the square root of 65. Hopefully you recognise the perfect square of 7 and 4. And that's all we're asked to do for part A. So let's move on to part B, where we're asked to find BH and round to 2 decimal places. So let's go back up and have another look at that diagram. So let's mark in BH. That would be this red line here. And clearly we have a right angle BH, BE and this line that's 2. So using Pythagoras' theorem, BH squared is going to equal BE squared plus 2 squared. So subbing in the values we already have, BH squared is going to equal the square root of 65 squared plus 2 squared. Squaring a square root gets rid of the square root. So we're left with BH squared is equal to 65 plus 4, which is equal to 69. Therefore BH is equal to the square root of 69. And if I put the square root of 69 into the calculator, type equals and spacebar, we get this number 8.30, so on and so forth. Now if I'm going to round this to 2 decimal places, that 6 obviously makes the 0 go to 1, so BH is equal to 8.31. Just note that if you weren't asked to do the intermediate step that we did in part A, you could go straight to my method, which is BH would be equal to the square root of 7 squared plus 4 squared plus 2 squared equals the square root of 49 plus 16 plus 4, which equals the square root of 69. Okay, those numbers there definitely add to 69. And we end up where we were anyhow. So I think my method is quicker, and this is how you do it in 3 dimensions. In fact, that's how you do it in as many dimensions as you want. But anyhow, we're at the end of the example, so pause the video now and do questions 4 in the new book and questions 5 in the old book. And I'll see you in the summary. Before we summarise this lesson, don't forget that there's some challenges at the end of the lesson. While they're optional lectures, I do expect you to attempt them. However, because there are 3, we're going to do these in a separate video that will be attached to the same OneNote. And as I said, I do expect everyone to at least try them. Anyhow, let's just summarise this lesson now. To be successful in this lesson, you will know the relationship between the square of the hypotenuse and the sum of the squares of the other 2 sides. Be able to apply Pythagoras' theorem to find a missing side length of a right angle triangle. And be able to identify right angle triangles in 3D objects and apply Pythagoras' theorem. Alright, so that's the end of the summary. Please come back for the challenges and I'll see you in that video. Bye.